Okay, simple harmonic motion, as this moves up and down, you can see from the GIFs on the Moodle page that the motion is very much like the movement of an object in a circle. So before we start looking at the equations of simple harmonic motion, which look like this, we're going to look at some circular motion definitions first. The first quantity that I'm going to define is something called angular frequency, or omega. Angular frequency is measured in it's measured in units of radians per second. So what's a radian first? A radian is a piece of a circle. It's like a piece of this. If this was a giant cake, imagine a piece of it that would look like this. The radius has to equal the arc here, okay? So if this arc that's cut out is a radius long, then what you have is a piece of a circle like this, and that piece of a circle is 1 radian, okay? So what is a radian? It's a chunk of a circle. And if you had to convert it into degrees, it would always come out to be 57, approximately, 0.3 degrees. You don't need to know that, but it might help you visualize it. Okay, so most of the quantities that we measure for circular motion and simple harmonic motion, we use the radian. So now we're going to look at some quantities that are to do with the motion of a particle. Imagine this particle here moving around a circle. There are 2 types of speed or velocity that we can consider. The first is, what is the actual velocity of this particle traveling in that circle? If you were in a car, maybe, that was spinning round in a circle, what we're considering is, what is your actual speed as you move around? Okay, now we're going to use a really basic idea. The total distance that you travel as you go round that circle is equal to the circumference. And how long does it take you to cover that entire circumference? Well, we can use the same quantity as we use for oscillations. It's 1 period, so t, period. How would we describe the circumference in terms of the radius, for example? So if I draw the radius here, what is that circumference? Well, we know that 2 pi r gives us the circumference over the period would give us the speed of the particle that's traveling in a circle. Because it's linear speed, the units would be meters per second to the -1. Angular frequency is rather different. The angular frequency is the angle that's swept out as you move across in a circle. So if you're moving along here, what is the angle that you are covering per unit time? So as you move further and further around the circle, this angle will increase. We can define that as the equation by considering what is an entire circle. So if we consider the angular frequency of an object traveling an entire circle like this, from there all the way around back, then the angle covered would be 360 degrees over, well, let's think about this. How long does it take for an entire cycle to happen? It's the period again. So this should do, but remember, we need to show omega, angular frequency, in radians per second. So this is not quite right. Let's try and express an entire angle in radians. If we go back to our definition of the radian, it's when this distance on the arc of the circle is equal to 1 radius, like this. So, this is 1 radian. How many radians fit on an entire circle? Well, that would be the same as how many radians fit around an entire circumference. Okay, now the circumference, we've already looked, is 2 pi r. So, how many radiuses are inside 2 pi r? Well, you divide 2 pi r by r, and it's 2 pi. Okay, so 360 degrees, or an entire circle, is equivalent to 2 pi. If you want to then extrapolate other angles, how much is 180 degrees? What do you think? It's actually pi. And 90 degrees, how much would that be? Pi over 2. Good. Let's go back to our definition of omega, angular frequency. Angular frequency equals, we've already said, 360 degrees over the period. And now we can replace that to give us the answer in radians. Omega, or angular frequency, equals 2 pi over t. And this time, all answers will be in radians per second.